Hello, in this video we will be discussing power functions and polynomial functions. In particular, we will be able to identify polynomial functions given an equation. We will determine whether the degree of a polynomial is even or odd, and if the leading coefficient is positive or negative, and we will use that information to determine the end behavior of a polynomial. Okay, so let's first start with a definition. A power function. A power function is a function that can be represented in the form x to the p, where the base is variable, that's x, and the exponent is p, a real number. So in this first question, we're just asked to identify all the power functions here. So this first one is x to the first power, so you can write that as where p equals 1, right? So this is, I'll circle it. It's yes, and I'll put the value of p next to it. So this is good. P equals 1. So y equals x is a power function. Here, y equals x to the second power. That's p equals 2 is a power function. Y equals x cubed. That's p equals 3 is a power function. So the first three are all power functions, clearly. What about this next one here? Well, we could rewrite this as x to the negative first power. So yes, this would also be a power function because p now is negative 1. Similarly here, we could write this as x to the negative 2 power. And so this is also a power function, p equals negative 2. B to the x looks like it might be a power function, but if you look carefully, b is not the variable. So this is not a power function. So not a power function. Clearly log is not a power function. Moving on to the x, radical x, we could write this as y equals x to the 1/2 power. Right? So in this case, p equals 1/2. So this could be considered a power function. And in this case, we have y equals the cube root of x, that's x to the 1/3 power. So we have p equals 1/3. So this is a power function as well, according to this definition, because p just has to be a number, right? And in this case, no, this is not a power function because that's an absolute value. It's really a piecewise function. Remember when we studied absolute value, it's a piecewise function of x, negative x. So it's kind of two power functions. It's defined by two power functions, but by itself, it's not a power function. Okay, so hopefully we have an idea of what power functions look like. Now we're going to consider graphs of power functions with positive integer exponents. So in group 1, you'll notice we have x squared, x to the 4th power, x to the 6th power, and x to the 8th power, right? Starting on the outside, moving in. And on the right side, you'll notice we have x, which is this line here, y equals x, going through the origin. Then y equals x cubed, y equals x to the 5th, and y equals x to the 7th. So even exponents, right? Over here, we have even exponents and odd exponents. So what's the difference between these two? Right? What do you notice? Well, I'll tell you one thing that jumps out at me is notice in group 1, since they're all even powers, all of the function values are positive or 0 here. So group 1 is positive or the function is positive or 0, right? In group 2, the function can be negative, right? But it could also be positive. So the function is positive and negative. And we should note that it's negative when you're on the left side of the y-axis, right? The function goes negative. Okay. Another thing I notice about group 1 is that it has a symmetry with respect to the y-axis. So not only are they even powers, they look like even functions, right? They're symmetric with respect to the y-axis. Group 2 is not, right? Group 2 is not. Group 2 looks like it's symmetric with respect to the origin, right? Because they're odd. These are odd functions. So these are even functions. Group 2 is symmetric with respect to the origin. They're odd functions. Okay? So there's some differences. Another difference I noticed too is in their end behavior. Notice as x gets infinitely large here, right, as we go in the positive x direction, notice these are heading up towards positive infinity. And it's likewise if we head in the negative infinity direction or negative x direction, it's also headed towards positive infinity. So for group 1, the end behavior right? The end behavior goes to positive infinity, right? For group 2, looks like it's going to positive infinity on the right and negative infinity on the left. So it goes to plus or minus. End behavior is plus minus infinity. Okay, so there's just some differences I noted. Okay. Okay, let's fill out this little summary of power function properties, really, and the end behavior, whether it's increasing, decreasing, positive or negative. Let's talk about the x-intercepts, y-intercepts too. So when n is even, right, as x goes toward infinity, the y values also approach infinity, right? Positive infinity, right? As x goes to negative infinity, the y values they still approach positive infinity because they're even powers, right? Okay, so that's good. Now, even functions, when x is negative, right, less than 0, is it increasing or decreasing? Well, let's look at these even functions. When x is less than 0, you're on the left side of the y-axis, right? Notice that we're decreasing, right? So the graph is decreasing. And when x is greater than 0, the graph is increasing, because you have this shape to it, right? Decreasing and then increasing. The graph is always positive for even functions, as we noted in our observations. The x-intercept, if it's just a straight up power function, is going to be 0, and the y-intercept is also 0. Okay. All right, so let's look at odd powers. Now, as x goes toward infinity, the y values, they approach infinity too. Positive infinity. However, as x goes to negative infinity, the y values approach negative infinity. Okay. Notice for odd functions, it's always increasing. You're always going up, right? You're always increasing. So increasing. When x is less than 0, the graph is, I would say, below the x-axis, right? Below It's negative, right? When x is greater than 0, the x is above the x-axis, right? And it still has a intercept, an x-intercept of 0 and a y-intercept of 0, right? Because it goes through the origin. Okay, so there's our summary of even and odd power functions. Okay. If we add a bunch of multiples of these power functions together, where the n is either 0 or a positive integer, then you wind up with polynomials, right? So a polynomial function consists of the sum of a finite number of terms, each of which is a product of a real number coefficient and a variable raised to a non-negative or non-fractional power. In other words, a polynomial is the sum of functions of power functions of the form ax to the n, where n is equal to 0, 1, 2, 3, and a is any real number. So they could look like this, right? So a polynomial in x, right, should look like maybe there's a constant term with a 0 power of x there, plus maybe another coefficient with a first power of x, plus maybe another coefficient with x squared, plus maybe another coefficient with x cubed. Maybe some of these coefficients are 0, some of them are, doesn't matter what these numbers are. They could be negative, they could be positive, they could be fractions, irrationals. But you wind up with a polynomial like this, right? Plus dot, dot, dot. And it's going to have some end power, maybe the nth power, right? So that would give us the highest degree in the polynomial is called the leading term, right? And this n is a very important number, actually. The degree of the polynomial n indicates that the polynomial has at most n roots. What does that mean? That means if we solve the equation, right? By the way, sometimes we put a little subscript here to indicate it's an nth degree polynomial, right? So if a polynomial an nth degree polynomial is set equal to 0, right? That means there are n possible, at most, there are n x values that will make the polynomial 0. Make the polynomial equal 0. So that's what that means, at most n0. So for example, let me add a page here. If I just give you let's say a third degree polynomial like this, right? Let's just say it's 3x cubed plus 2x squared plus 1, right? And if we set this equal to 0, 3x cubed plus 2x squared plus 1 equals 0, we know this will have at most, might have less real roots, at most 3 solutions. And sometimes those solutions are called roots of the polynomial, right? Or zeros of the polynomial, because that's what makes the polynomial 0. So it has at most 3 real, I should say 3 real solutions, because there could be complex number solutions also. Okay, let's keep going. Okay, so in this next exercise, we're given some functions, and we just want to determine why this is not a polynomial, right? So these functions, I'm telling you, are not polynomials. Why are they not polynomials? Well, this one is not just the sum of power functions, right? This has a square root in it. The square root makes it not a polynomial. Here, it has a negative exponent. Right? For polynomials, remember, we want our values of n, our values of p to be greater than 0 or equal to 0, right? Just to go back to the definition, remember, n has to be 0, 1, 2, 3, right? If it's ax to the n, it is n. Okay, so this has a negative exponent, and this one has a fractional exponent, right? So these are not polynomials. Okay. If we add these three terms, 7x squared, 1/3 x to the 4th, and -5, we wind up with a polynomial, right? This is a polynomial. Notice the 5 is a constant, but you could think of it as x to the 0 power, which is just 1, right? Remember, x to the 0 power is 1. So we call these terms of the polynomial, right? If 7x squared is a term of the polynomial, what's another term? Well, 1/3 x to the 4th is a term, and also -5 is a term, right? The leading term of this polynomial here is 1/3 x to the 4th. What do you think is meant by leading term of the polynomial? Well, you might have heard this before, but a leading term has the highest degree of x. Right? So x to the 4th is higher than x squared, 4 is greater than 2 and 0, so 4 is the leading term, right? We say the degree of the polynomial is 4. What do you think is meant by degree? Well, that's also, it's just the highest degree, right? The highest power of x. The leading coefficient of the polynomial function is 1/3. Leading coefficient, what does that mean? Well, that is just the coefficient of the highest degree term.